Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation on this topical MCQ, a 5-question series on what I have classified as topic 4, states of matter. That includes the gas laws and how they work as the ideal gas equation. Yeah. So a lot of questions in this classification topic involve ideas of ideal gases. So for example, like this question. So we know that Boyle's law says that pressure is inversely proportional to the volume of the gas at constant temperature. So that is Boyle's law. And therefore PV equal to constant at constant temperature. So we expect PV to be constant for an ideal gas at constant temperature. So you can see that most of these gases are quite okay at low pressure. So at low pressure, they follow mostly PV as constant. However, some of them are very much deviating so much from the constant line we're expecting, meaning to say this is very least ideal. Out of the three X, Y, and Z, this is going to be the least ideal. And between X and Y, I would have thought that Y are closer to the constant line. As the pressure slowly increases, you can see that for Y it remained much closer to the linear constant line there for ideal gas compared to X. So X is the second least ideal, whereas I would imagine that Y being the most ideal. So the least ideal is going to have the strongest intermolecular force, whereas the most ideal is going to be the weakest intermolecular forces. Between these three, ammonia and hydrogen gas and nitrogen gas, we can imagine them all having van der Waals, okay, because they all have electrons in their molecule. In terms of permanent dipole, so we know that ammonia is polar because it's got 3 bond pair and 1 lone pair on the nitrogen. So there is the dipoles are not symmetrically distributed. So the charges are not symmetrically distributed, they don't cancel out, so you get a polar molecule. But hydrogen and nitrogen are non-polar because they have the same electronegativity. Right? And of course, in terms of hydrogen bond, ammonia is the one that can form hydrogen bond, not only because it's polar, but also because it got hydrogen bonded to the highly electronegative elements, such as nitrogen, fluorine, and oxygen, and you got a lone pair on the highly electronegative nitrogen there. Okay, because these are non-polar to begin with, they wouldn't even form hydrogen bond. All right. So between hydrogen and nitrogen, so how would you decide the strength of their van der Waals? We look at two things. One is the total number of electrons in the molecule. So hydrogen only has 2 electrons in the molecule. Nitrogen has 7 plus 7. It has 14 electrons in the whole molecule. Okay, so hydrogen molecule is going to have the weakest intermolecular force. So we say the most ideal is going to be hydrogen. So Y is going to be hydrogen. The least ideal is going to be the one with hydrogen bond, which is ammonia. So Z is going to be ammonia, which means the other one has to be nitrogen. All right. That can very easily be a structure question where they ask you to reason it out or to explain whichever one is which, and you have to talk a lot in terms of the intermolecular forces. Yeah. So here they're asking you when ice is heated to very high temperature. So obviously the H2O will become steam, and steam is H2O gas. So we can use the ideal gas equation. So when you heat up the 1 gram of ice, mass is being conserved. So all the 1 gram of H2O is going to give you 1 gram of the H2O gas as well. Conservation of mass, right? When you write this equation, what does it mean? It means that, mass is being conserved. Whatever is here forms whatever is on the right hand side. That's why you conserve the mass when you write a balanced equation, right? So this is the one we're going to apply the ideal gas equation onto. So PV equal to nRT. So they want volume. So N is mass over mR. So there's mRT over mR times P. Okay, the question now really is, you need to work out what is what. The mass of the gas, okay, the steam, is going to be 1 gram, based on what we said about conservation of mass. The The R is at 0.31 joule per Kelvin per mole from the data booklet, as I'm sure you know where to find it. The temperature is given in degrees Celsius. You need to convert that to Kelvin. You need to add 273. So they give me 596 Kelvin. And then what else? The pressure is given as kilopascal, and we know that we want it in Pascal because 1 Pascal is 1 Newton per meter square, and we want it to be in standard unit, Newton, which is Newton, which is Newton, and then per meter square, which is a standard unit. Yeah, so it'll be 101 times 10 to the 3 Pascal, which is the same as Newton per meter square. So that's our standard unit there. The next bit really is, well, the MR. Well, the gas is H2O, so the MR is going to be 18.0, which is 2 for the hydrogen. 2 times 1.0 plus 16.0. Put all that into your equation. Be aware that this equation with all these units, the volume will be given in meter cube. This is in dm cube, but I will worry about that later on. So 1 gram times 8.31 times 596 divided by 18 divided by 101 to the power, well, times 10 to the 3. I get 2.72 times 10 to the minus 3. That is meter cube. So units are very, very important here, yeah? How would you decide which one is which? You can tell 1.3 is definitely out. 48 is definitely out, okay? But which one is which? That's what you need to decide. 1 meter is equal to 100 cm. 1 cm is equal to 10 to the power minus 1. Oh, sorry. It's very better if I do it this way. 1 decimeter is 10 cm. So therefore, 1 meter is 10 dm. 1 dm is 10 cm. So if we have 100 cm, we have 10 dm. So I'm just doing the equation, all right? That's the meaning of the term equal, which I'm sure you know from your primary school mathematics, what equal means. So I'm going to cube both sides. 1 cube is 1. Meter cube is meter cube. 10 to the 3 dm cube. I got my conversion factor there. So if I convert it to dm cube, I need to multiply by 10 to the 3. That becomes dm cube. That will give me exactly 2.72 dm cube because the 10 to the 3 and 10 to the minus 3 cancel out, which means this is the closest answer, all right? So next bit is about the gas laws again. So this is they don't tell you what is constant, except that you know Boyle's law. So Boyle's law says pressure is inversely proportional to the volume of a gas. That is at constant T. So PV equal to constant at constant temperature. Okay, and so PV should be a constant at constant temperature. So it should have been a constant. Okay, so that is incorrect. That should be right. Again, PV should be a constant. So that is incorrect. That should be right. This is incorrect. So P against V is an inversely proportional graph. So this is what it will look like if you do the Boyle's law correctly. Meaning to say you're left with D, and that is the Charles law. Charles law of gas says that the volume of a gas is directly proportional to the temperature of the gas, but that has to be in Kelvin, and that is at constant pressure. So that is what Charles law says, yeah? When the pressure is constant, the volume is directly proportional to temperature. This is a very naughty question. It should have been in Kelvin in order for it to be appropriate, because it cut through 0, okay? Anyway, next question. So we have a constant temperature there. So this kind of question is better if you think about, I don't know, if I have a valve there, and then you have two bulbs, X and Y. You have 5 dm cube, you have 12 kilopascal, you have 10 dm cube, you have 6 kilopascal. So this is like a valve. If you open up the valve and if you connect them together, then your total volume is going to be 5 plus 10, which is 15 dm3. So now your final pressure is what you want to find, which is your P total, okay? And we know that PV equal to constant at constant temperature. So that is your Boyle's law, which I stated in the previous question. So Boyle's law, the inversely proportional relationship can give you PV equal to constant. So what happened then is the constant here plus the constant there will be equal to a new final constant. So where you have Px Vx plus Py Vy will be equal to P total V total. Okay, so we're not going to concern ourselves about units that much here, because if you look at X, that is 12 kilopascal multiplied by 5 dm3 plus 6 kilopascal multiplied by 10 dm3. You want the P total, and then the V total is 15. Because I have used the P total of kilopascal and kilopascal, the P total will be in kilopascal as well, because it's going to be kilopascal times dm3. So what I'm talking about is kilopascal dm3 plus kilopascal dm3. dm3. Then this would be kilopascal times dm3. So it's about the bookkeeping of the units, yeah. Anyway, if I do the maths correctly, I will get 12 times 5, which is 60, plus 6 times 10, which is another 60. So that's 120. Move the 15 underneath because it's multiplied here, so it becomes divide to the other side. 120 divided by 15 give me 8, and the unit will be 8 kilopascal. So don't forget your units, yeah. All right. So this is the last question of this 5-question series. Behave most like an ideal case. So that means the least of the weakest intermolecular force, or you can say the most negligible. I think least is probably not a great word because you can't really count intermolecular forces, yeah? The weakest intermolecular force or the most negligible one, all right? So when you look at carbon dioxide, so it's non-polar because you get a symmetrical distribution of charge, the dipoles cancel out. Helium is also non-polar, but what is important is monoatomic. It exists as single atom. You, of course, do not have to write all of this down. I'm just outlining my thought process to you so that you can see what is going on. This is also non-polar, but again, the difference with helium is diatomic. The nitrogen is also non-polar, and this is diatomic as well. So you have a dilemma here, you see. All of these are non-polar. So all of these don't have hydrogen bond or whatever, but that's not the idea here. The idea is these are all non-polar, so they only have van der Waals forces, but you need to consider the strength of van der Waals, which is to do with total number of electrons in the molecule. A lot of students get that, but they miss out the second bit. It's N. It's not or, it's N, the size of the atom or the molecule. Okay, so this one has 6 electrons, this one has 8 electrons, this one has the most number of electrons compared to any of these. This one will have the strongest van der Waals. Moreover, it's got 3 atoms, the size is going to be bigger than 2 atom or 2 atom or 1 atom. Okay, so this is going to be the strongest van der Waals, and therefore I can think about this being the least ideal out of all the 4. All right, and then this is the next one, because it's also got more electrons than this. It's got 7 and 7, 14, although it's lesser than that. So this will be the next least ideal. And then now between this and this has got 2 electrons, and this has got 2 electrons. One here, whereas this is single atom, it's got 2 electrons. How would you compare your van der Waals? You can't if you just look at the first factor, which is why you need the second factor, which you also learn in school, which of course is also in your textbook, which of course a lot of you would probably forget about this second factor. All right, this is a 2-atom molecule. It's always going to be bigger than helium, so the size is bigger because, well, you know, it's got 2 atoms instead of 1 atom. So therefore, stronger van der Waals. So we are looking at these having the weakest van der Waals compared to hydrogen, compared to the rest which have more electrons, and therefore helium will be the most ideal out of all 4 options given here. So this is the end of this 5-question MCQ tutorial. So I hope it helps in you addressing your knowledge and understanding as well. That should hopefully help you with your theory paper. If you find this useful, please subscribe to the channel. Spread the words about the channel with your friends in your group chat and your teachers. And yeah, I'll see you in the next video. Thank you for watching.